Apple products are expensive. I mean, come on. For such little innovation, they charge you so much more for each new generation of iPhone. No more, I say. It's time we did something about this. We should, that's it. Let's make our own iPhone, out of apples. So an iPhone consists of 33 grams of iron, 6 grams of copper, and a bunch of other metals. I brushed aside the rest because the limiting number of apples we need for an iPhone will be based on either the iron or copper content. By that I mean, we need more apples to meet, say, the iron quota than we do for, say, the calcium quota. And assuming we can extract everything we need from each apple with no waste, then the amount of apples will depend solely on the amount needed for the iron. Oh, and also, some things found in the iPhone just aren't in apples, like gold, silver, radon, gallium, polonium, yttrium, terbium, europium, bromine, dysprosium, indium, and like another third of the periodic table. This isn't like Minecraft, unfortunately, and golden apples aren't real. So, we have to take some creative liberties. An average medium apple has 0.24 milligrams of iron and 0.054 milligrams of copper. Doing some simple maths, 33 divided by 0.24 times 10 to the minus 4 gives us 137,500 apples needed to meet the iron need and 111,111 to meet the copper need. Hence, we're going to need a minimum of 137,500 apples to get enough raw materials. So, assuming we have devised some way to extract all the elements from the apple, as well as have the energy required to do so, whose contribution to the bill we are going to be ignoring, we have our iPhone. Perhaps it could be achieved practically through some combination of boiling the apples in a strong acid, and then a series of displacement reactions to separate the pure metals from their salts. Anyway, here's our iPhone. Boo, it sucks. But wait, of course, we haven't charged it yet. Silly you. We could try and make an Apple battery, but we'd have to connect quite a few in series to get a significant voltage. Not to mention the internal resistance will make it quite slow charging, and presumably you want something up to snuff with those money-grubbing lizards at Apple. So let's say we want our charger to charge our Apple phone from 0 to 100% in about 3 hours. The voltage source needed is around 5 volts. So what can we do? Let's make some electrochemical cells. From the standard E0 values for reduction, the largest potential difference that can be achieved from the materials in an apple is through the reduction of ferrate 6 ions and the oxidation of solid potassium. The equations for each of these processes are on screen now. Balancing the number of electrons and then combining, we get this overall equation. The standard potential difference we get from this is 2.2 minus 2.931, which equals 5.131 volts. Perfect. But wait, that is under standard conditions, 1 molar quantities, which will be unlikely to have. If only there was a formula for this. I don't know, I don't want to have to buy all these chemicals just to work this out. I don't make any money from this anyway, so... Oh, what's this? Oh, thanks, Nernst. So, using this equation known as the Nernst equation, E equals E0 minus RT over NF, all multiplied by ln Q, where N is the number of electrons transferred and Q is the reaction quotient, similar to the Kc. In this case, R and F are just constants to make the units work out. From our balancing, we know the total number of electrons transferred is 3. To work out the reaction quotient, we need to do a little bit of algebra. The reaction quotient only depends on aqueous or gaseous species, so we can ignore the potassium as it is a solid and the water as it is a liquid. So the reaction quotient will eventually equal the Kc, so we can just work out the Kc. To do this, we need to work out the moles at the start. Making life easy, let's say the moles of ferrate ions is 1, then we can do the balancing and say 8 moles of H+. Then let's say the change in ferrate ions is X. Using the balance formula, the moles at equilibrium are given by these expressions that are dependent on X. So, plugging these into our expression for Q, we get this. And then we can exchange Q for Kc to get this. And then we can simplify it to get this. The change in our quantities shouldn't be 0, because then we haven't got a reaction, and it also can't be 1, else the denominator will be 0, and then the Kc is undefined, tending to infinity. So let's change it so that X is equal to 0.99 moles. Q is then equal to 1.546 times 10 to the 12 multiplied by V to the power 8. Setting V equal to be 1 decimeter cubed will simplify things down. So now, Just doing the maths, we get an E value of 4.89 volts, which is close enough to 5 volts. Just for your information, iPhone batteries are rated at 1500 milliamp hours, which is equivalent to 5400 coulombs. Now, let's work out how many apples we need to form this electrochemical battery. Since we chose 1 mole of ferrate ions, it's rather trivial to get the fact that we need 56 grams of iron, and doing the same method as before, that translates to 233,334 apples. Whilst it should be obvious that to meet the potassium need it should be less, here it is anyway. And for the water, turns out that 1 apple is actually more than enough. So, for the battery, we need more apples than for the phone itself. Interesting. Totaling it all up, we find that we need 370,834 apples. From Tesco, a 6-pack of apples is £1.60. 370,834 divided by 6 is 61,805.7, so that means we need 61,805 6-packs and then 1 loose apple, which is an extra 54p. The total is then going to turn out to be £98,888 and 54 pence. The average iPhone 13 is £679, so this mass of apples is 145.6 times more expensive. So, definitely worth it. If you were to make this volume of apples into a sphere, well, let's do the maths. The volume of 1 apple is 187 centimeters cubed, or 1.87 times 10 to the minus 4 meters cubed. Multiplying by the total number of apples we need, we get a volume of 69 meters cubed. Nice. The volume of a sphere is 4/3 pi r cubed, so the radius of the giant apple sphere is 2.55 meters. Hence the diameter is 5.1 meter, and that's 3 times taller than the average male. So quite a big sphere of apples. Thanks for watching. Subscribe if you enjoy. I have many more absurd videos like this one coming up.